All right, guys, in chapter 3, the first PowerPoint, we have one more problem to do. It's the last two slides of the PowerPoint, so it's slide 35 and 36. It's kind of a application topic. You know, we've learned about mole relationships and chemical reactions, and you can use the amount of a reactant to find the amount of product that can be formed or how much of the other reactant will be used and all that kind of stuff. So here's a problem that kind of combines the problem we just did about finding the empirical formula with our stoichiometry stuff. So it's kind of a tough problem, but if you can understand the logic that we use in this problem, then I feel pretty good that you're really starting to get this material really well. So the idea is we're burning a compound that contained carbon, hydrogen, and oxygen, but I don't know the formula, so I don't know what any of the subscripts are for the carbon, hydrogen, and oxygen in that compound. But when I burn something, and it's something that, again, in the second PowerPoint for chapter 3, we're going to get into the types of reactions. So one of the types of reactions is combustion, which is where you take some kind of a burnable fuel. So that's my fuel. I'm going to react it with oxygen from the air. I usually have to kind of light it with a match or something to get the combustion going, or at least to make it happen a lot faster than it would in nature. So I light the fuel, I burn it with oxygen, and if it's a hydrocarbon, which means a fuel that's made up of carbon and hydrogen, then my products are going to be carbon dioxide and water. Okay? Now, we're going to do some manipulation here that says, basically I have a fuel that I don't know what its formula is, but if I burn it and measure how much CO2 and H2O are produced, I'm going to be able to back calculate the amount of carbon, hydrogen, and oxygen that were in that compound. Okay, so that's our idea we're trying to solve. So basically the problem gives us that when they burn, it says this is the amount of water and CO2 that are produced for each gram of the compound burned. So basically if I burn 1 gram of the fuel, I'm going to use some oxygen from the air as well, but I'm not really worried about that. But it's 1 gram of the fuel fully burns. It'll produce 0.6 grams of water and 1.467 grams of CO2. So from those numbers, I should be able to use the amount of water here, and I should be able to figure out how much hydrogen's in there. And then I should be able to figure out from the amount of CO2, I should be able to figure out how much carbon's in there. And then if I know how much carbon and hydrogen I have, I should be able to subtract those numbers from the original amount of the fuel to see how much oxygen was in there. I have to find the oxygen indirectly because some of the oxygen that's present came from the fuel, some of it's going to come from the air, and since I don't know how much oxygen comes from each place, I can't find that as easily as the hydrogen and carbon. But luckily, with only 3 things, if I can solve for 2 of them, then it's easy to get to the third one because I know the total weight. Okay, so let's start working. I want to go from grams of hydrogen, grams of water. I want to get to, I'm going to have to do 2 things. I'm going to have to know the moles of the hydrogen and the grams of the hydrogen. Because to get the empirical formula, I'm going to have the moles of all the elements like we did in the last problem on the previous video. But then to get the amount of oxygen, I'm going to need the grams of hydrogen. So I'm going to go first to the moles of hydrogen. And then once I have that, then I'm going to go to the grams of hydrogen. Okay? And I'm going to do the same thing for carbon. From the CO2, I want to find the moles of carbon. And then once I have that, I want to find the grams of carbon. Okay? So, let's do one thing at a time now. I want to go from the grams of hydrogen to the moles of hydrogen. Excuse me, grams of water to moles of hydrogen. Now, water is a different substance from hydrogen. I know they're related to each other, but they're not the same. So on my mole map, I'm going from the grams of compound A to the moles of something else. So this would be moles of B. If you look back at your map, from grams of A to moles of B, that's 2 steps. And again, I really would like for you guys to kind of have a copy of the mole map with you all the time so you can kind of think about what you're starting with and what you're finishing with and decide which steps you're going to do. Until you kind of get the hang of it and start to kind of see these things a little more clearly, it's really good to kind of have that guide to look at. Okay? So, to go from grams of A to moles of A, I divide by the molecular weight. So for water, that's going to be 18. Again, if I watch my units, grams cancel grams, so that'll give me the moles of water. And then I need a relationship between A and B. That's my ratio. Well, what's the relationship between water and hydrogen? Well, this is back to where if I look at the formula of water, there are 2 hydrogens in each molecule. So I'm going to write down in one H2O molecule, there are 2 hydrogen atoms. So that's going to cancel out water and give me moles of hydrogen. So at this point, if I were to work it out, let's see, 0.6 divided by 18 times 2. It's going to be 0.06667. You just have to round it off somewhere. Okay? And then I'll do the same thing with the CO2. I'm going for moles of carbon here, so the first step, divide by the molecular weight, is 44 grams of CO2. And then my relationship between CO2 and carbon, well, in one CO2 molecule, there's 1 carbon atom. So that's a 1-to-1 ratio. One CO2 molecule contains 1 carbon atom. So all I have to do is just divide the original number by 44. I got 0.0333. All right. Now, at this point, if you remember, to find the empirical formula, it's going to be the ratio of the moles. So I have the moles of hydrogen, I have the moles of carbon, but what I still need, I need the moles of oxygen. But at this point, I can't use these numbers to find the oxygen because remember, some of the oxygen came from the fuel, but some of it came from the air too. And there's no way to distinguish those by doing these calculations because when I look at the water and the CO2, I don't know where the oxygen came from there. Okay? So what I'm going to do instead, if I change the moles of hydrogen and moles of carbon into grams, I know the original compound weighed 1 gram. If I subtract these 2 numbers, it'll leave the grams of oxygen. So I'm going to use these 2 numbers, take away from 1 to get this one, and then I'm going to go back to the moles over there. Okay? So for carbon, I'll multiply the moles times the atomic weight of carbon is 12. So times 12 is going to give me basically 0.400 grams of carbon. For hydrogen, the molecular weight of hydrogen is 1. So I don't need to do that one. It's going to be 0.0667 grams of hydrogen. So now those numbers I'm going to subtract from the original compound, 1 gram that I burned. I'm going to take away the hydrogen and carbon, and it's going to leave oxygen. So 1 minus those numbers. And it gives me 0.5333. So now, again, to get the empirical formula, it's going to be the mole ratio. So now I got to get the grams of oxygen back to the moles. So from grams of oxygen, divide by 16 to get moles. And it's going to be 0.0333. Now, at this point, I've got my moles. If I can look at that and figure out the ratio, I'm done. I could write my ratio and be done. If you can't see it, then you pick out the smallest number, divide that number into all 3 of them, and that should kind of clean the ratio up for you. But when I look at this, these are equal, and that one's twice as big. So I know that this is going to be C1H2O1. That's my chemical formula, which you don't really have to put the 1s. I could just put CH2O. That's the actual empirical formula that we're looking for. Now, there's no way to know what the molecular formula is unless they give me the molecular weight, and then I can look at this and look at the molecular weight and figure out how they relate to each other. Okay, so that's the end of the math part of chapter 3. Okay, Next video, we're going to get into writing more reactions and practicing that kind of stuff. So the next set of videos are actually going to cross between chapter 3 and 4, but we'll talk about that in a minute.